In this video, we're going to cover one of the most powerful tools in probability, Bayes' theorem. As we can see from our notes, Bayes' theorem helps us calculate the probability of an event based on partial or conditional information. Here's what we need to know to apply Bayes' theorem. P of f, which is the prior probability of f, P of E given f, the probability of E given f, and the P of E given not f, and the P of not f. Here's Bayes' formula. This may look intimidating at first, but let's break it down. The numerator is the joint probability of E and f occurring together, and the denominator ensures we're considering all possible ways E could occur. Now let's work through problem 1 in the textbook. The problem states that suppose E and f are events in a sample space, and P of E is a third, P of f is a half, and P of E given f is 2/5. Find P of f given E. We can use Bayes' formula. P of f given E is equal to P of E given f times P of f. That repeated, P of E given f times P of f plus P of E given not f times P of not f. That can be simplified to P of E given f times P of f all over P of E. Now we can plug in the numbers given to us in the question. So P of E given f is 2/5 times P of f, which is a half, over P of E, which is a third. That gives us 3/5. So we have found P of f given E, which is 3/5.
Now let's go over some common applications of Bayes' theorem or reasons why we would want to use it in real life. This includes in medicine when testing positive and determining the probability of the person actually having the disease. It's also useful in weather for determining how likely it is that a weather forecast is accurate, and financially, it allows us to make decisions on whether or not to invest based on previous market patterns. Of course, there's many other examples, but these are the main ones. Now, let's try an example. This is problem 5 from the textbook. It reads, a new test has been developed to detect a disease that affects 1 in 10,000 people. The test is such that the probability that the test is positive when given to a person with the disease is 0.99, and the probability that the test is positive when given to a person without the disease is 0.005. What is the probability that a person who tests positive actually has the disease? Okay, let's use the given information to plug that into the formula. So first we're going to represent the events with letters. We know that the person tested positive, and therefore that is going to be our E. And what we want to find out is if they actually have the disease. So let's set that equal to F. Now let's write out our formula to see what information we need to find. So the formula is P of F given E equals P of E given F times P of F. That over first the same expression, so P of E given F times P of F plus P of E given the complement of F times P of the complement of F. Now let's find the information we were given in the problem. So the disease affects 1 in 10,000 people, and that is going to be the value of F. So P of F equals 1 out of 10,000, which equals 0.0001. Next, it says that a true positive result is going to be 0.99. So that is going to be P of E given F, the probability of them testing positive after actually having the disease. On the contrary, we have the probability of a false positive, so P of E given not F equals 0.005. And last, let's also find out the probability of them not having the disease at all. So that's P of the complement of F, which is equal to 1 minus P of F, which equals, if we subtract 0.0001, that's 0.9999. Now that we have all of our information, let's plug that back into our equation. So this is simply 0.99 times 0.0001 over 0.99 times 0.0001 plus 0.005 times 0.9999. If we use a calculator to calculate the final value, we are going to get for this problem 0.0194, which is equal to about 1.9%. This seems like a very low figure. However, if we take into consideration the rarity of the disease and the relatively high false positive rate, this figure makes sense. Next, let's quickly go over generalized Bayes' theorem, which is basically an expanded version of our previous formula. It says, suppose F1, F2, and events up to Fn are mutually exclusive and exhaustive events, such as the union of all of them equals the entire sample space. Then, for any event E, the probability of any single partition out of E equals P of E given Fi times the probability of Fi over the sum of P of E of Fj and times P of Fj. And this version extends Bayes' theorem to where the event space is partitioned into multiple mutually exclusive causes rather than just two in the previous problems. So let's start out with what we know and try to derive this formula. So first, let's write what is on the left side using just the basic form of Bayes' theorem. So this is a probability of f of j given E, and that would equal to P of E given f of j times the probability of f sub j all over the probability of E. Okay, so for the next step, we're going to use the hint to expand the denominator. So because E is equal to the addition of all these terms, we can write it as P of E equals the sum of all of them, which also equals the sum of, and we're going to use the multiplication rule. So this is E given f sub I times P of Fi. Now let's sub this back into the denominator. So P of f sub j given E equals what we had written before on top. As we can tell, it already matches with what's given in the formula. And we're just going to put our summation down below. And that is it. We have arrived at our final step. So we have fully derived this formula, and that is the end of the proof of generalized Bayes theorem.
Now let's talk through problem 23 in the textbook. This problem states that suppose E1 and E2 are the events that an incoming email message contains the words W1 and W2 respectively. And it asks us to show that this statement is true using Bayes' theorem. The general form of Bayes' theorem for this scenario is P of S given E1 and E2 is equal to P of E1 and E2 given S times P of S over P of E1 and E2. Let's expand the denominator. The denominator P of E1 and E2 can be expressed using the law of total probability. So let's write the same numerator. And the denominator becomes P of E1 and E2 given S times P of S plus P of E1 and E2 given not S times P of not S. A key assumption in Bayes models is that the presence of words W1 and W2 are conditionally independent, giving whether the email is spam or not. So this means the P of E1 and E2 given S is equal to P of E1 given S times P of E2 given S. And P of E1 and E2 given not S is equal to P of E1 giving not S times P of E2 given not S. Substituting these back into the formula, we get P of E1 given S times P of E2 given S times P of S over P of E1 given S times P of E2 given S times P of S plus P of E1 given not S times P of E2 given not S times P of not S. The given formula appears to omit PS and P of not S. This is because spam filters often assume that P of S is equal to P of not S, which is equal to 0.5 equal to prior probabilities, causing these terms to cancel out. The formula represents a normalized likelihood ratio where the priors are absorbed into the conditional probabilities. So the simplified formula cancels out P of S, and P of not S, which gives us P of E1 given S times P of E2 given S over P of E1 given S times P of E2 given S plus P of E1 given not S times P of E2 given not S. And this is the same as the statement given in the problem. Thank you for listening.